Charging battery.
Wrong screen and started out on mute. We're doing great so far. Good evening, minions. This is how I would always greet my classes when I was teaching labs or other things. Because I'm strange, I guess. Yeah, I just never wanted to be one of those kind of like boring instructors. The ones who just come in and say hello class, or just some other just painfully generic greeting or start to their teaching. And certainly I had plenty of professors like that. People who didn't really take joy in teaching, but then there was one professor who always really enjoyed and has greatly influenced my teaching style and genuinely just like my sense of humor as a whole, because he's very just like kind of sarcastic, very dry sense of humor, uh, but just lovely and sarcastic and all those good things. And I remember the first course I took from him, and I took more chemistry from this prof than from any other, which I think was largely to my benefit. But I remember the first class that I took from him. He sent out an email to the class, as you generally do at the beginning of the semester, just to get everyone oriented. And his opening line was "Greetings, Earthlings," and I always appreciate that because I paid attention to what he said after that, and it was generally worth doing. Yeah, so when I started teaching, I didn't want to just have a boring, outrageously generic lead in to what else I was going to say. I wanted to capture at least some attention, or if nothing else, to hello Ross, nice to see you. Thanks for following. So I was just talking about this professor who was just would greet people in weird ways, and so I tried to do that when I started teaching, and so I just decided that my students were to forevermore be referred to as my minions. So my first email to my first class went out, and it said, "Greetings, minions." Um, and this has become a well known thing, as I've now taught kind of like oof, been going for 8 years and taught probably 200 to 300 students or so. So there's a lot of students at the uni who still refer to themselves as my minions. And, I took a chem module in my first year. A chem prof would call his PhD teaching assistants his elves. I really like that. Yeah, it's fun because I mean like it's how inaccurate is it really? Because you can just kind of tell them what to do, and like good little elves, good little minions, they'll just kind of go and do it. Um, so yeah, I've definitely taken chem from people who are a little more a little interesting to listen to. From that's okay. Everybody's got their own style. Everybody is going to be super enthusiastic. Um, Although I will say it makes a big difference. The effectiveness of learning um, when the professor is a history of agriculture, and it was exactly the material was just bone dry. The, the professor was so very into this. Was just so happy to be there. Um, that just it made it very tolerable, especially considering this is a 3-hour evening class. It went from 6 o'clock to 9 o'clock, and you just can't talk about the history of agriculture for long, and everybody's attention. It doesn't work. But this professor was wonderful, and I really appreciated that. I made it totally great. Sir Andrea Sella, lecturer, bless absolutely. We absolutely professors who try to make it a good as well as an one. But I'm going to stop just talking about random stuff, and we'll get into doing some chemistry. Since I've got somebody new with me, hello and welcome. My name is Nathan. I am a PhD student. I'm probably about 3, maybe 4 months away from graduating, so I'm just about at the end here, and I am planning to get into teaching after my degree is done, because I just really enjoy it, and so this is one way I figured I could do it, because I also believe that knowledge should be free, and an informed society is a cohesive and prospering society. So this is my my little corner of science communication on the interwebs. Mostly it's aimed at people who are taking chemistry at the university level, and I'm always very happy to take questions, or just like, can you talk about this subject for a while? I will very happily do so. But it's very much intended to be an accessible kind of a delivery of science. So I will be explaining things as I go. It might not be very fast, but should be pretty all right. Yeah. Other than that, if there's no questions, I've always got problem sets and stuff that I'll work through and talk through my approach to doing these things. So yeah, just let me know if there's anything in particular that you're interested in. But for now, we can, just one moment if you please. There we go. All right, so here's what we were working on last day, which was Friday. We were going over classifications of carbon substrates. And so what I mean by carbon substrates is, if you're looking to do a reaction with with a particular compound, it'll usually happen at things called functional groups, which are things that are generally just not carbon. Um, and and it's important to know how to classify the any carbons that we need to be talking about. For this is important in things like naming, in things like hello to you, my love. Things for like naming compounds, or doing any sort of reactions. This comes in heavily in synthesis, retrosynthesis, and just like looking at things like substitution or elimination reactions. It's important to a lot of different things. And so we can classify them as primary, secondary, tertiary, or quaternary. And so primary just means that the carbon you're talking about is attached to one other carbon, and then three things that are not carbon. These can be hydrogens, these can be oxygens, these can be halogens, whatever you'd like. And these can also be denoted as like first degree carbon. So first degree, primary, same thing. Secondary or second degree carbons are a carbon that is attached to two other carbons and two things that are not carbons. Tertiary carbons are attached to three carbons and something else. And as you may be suspecting at this point, quaternary carbons are just attached to four other carbons. This classification system only applies to tetrahedral carbons, that is, carbons that have four single bonds to other things. Because if we step outside of that classification, we can get things like this, which is not any of the above, so this is a carbon that is on a double bond. So it's an sp2 carbon. It's got a double bond in it, and so it has a different geometry. And I would, generally these are called vinyl carbons. IUPAC. That's right, because IUPAC just goes out of their way to make our lives tedious. But that's okay. We like IUPAC for most things. Okay, so we got through most of these. Now for this one, let's zoom in a little bit to look at this. So we're talking about the carbon on a benzene ring, and so this one is attached to two other carbons, one hydrogen, but it also has a double bond in it, which is sort of true because this is a benzene. Don't worry about it. But the point is, this is not a tetrahedral carbon. This is a trigonal planar carbon. This is a flat geometry, and so it cannot fall into that classification system. So this is also none of the above. But if you're going to call it something, call it an aryl carbon. All right, and this guy over here. Whoop, that is not what I meant to do. There we go. That's better. Okay, so carbon in a molecule of methane, CH4, technically also does not fit into this classification because it is attached to no carbons. So we do not call this a 0th degree carbon. What we do call this is methyl. So this is a methyl carbon. Yeah, I don't have a whole lot else to say about that, really. All right, and in the margins where I have managed to not fill it up with other things. Don't actually remember what that was about, but it's fine. I don't think it was important. So we're looking at this carbon here. Now you can try to look at that and come up with a just the classification of that in your head. I can do this because I have been doing this for a long time. About 12 years I've been studying this stuff, so that looks fine to me. However, if you have not been doing this entirely too long, then it may be helpful to just draw this out. So I'm going to start from this end. So we start with that terminal carbon. It's attached to another carbon. is attached to another carbon. And what this here means, the reason that this is in brackets, so this says two CH3 groups. And the implication in this kind of like structural formula that they've given is that there's two CH3 groups, and both of them are attached to this carbon. And so that looks like this. Kind of like that, because I'm bad at drawing with a mouse, but that's okay. Yeah, and so I'm just going to be lazy and draw the hydrogens out like this. This one I'm going to draw fully, H2, H3. So yes, because we are looking at this carbon. Yeah, so it's very helpful to just draw the molecule out fully. And as I will always say, when you're doing OChem, if you get stuck, draw stuff. So if you look at that and you're not quite sure what it is that you're looking at, just draw the whole molecule out, and it becomes fairly easy. So if we look at this carbon, and we're trying to assign it primary, secondary, tertiary, or quaternary, then of course the key thing to look at is how many carbons is this attached to. Well, it's attached to 1, 2, and 3 carbons and 1 hydrogen, which makes this a tertiary. Okay. Cool. Alright, so that is that section now done. Classify each alkyl halide or alcohol as primary, secondary, tertiary, or none of the above. I don't think I feel like doing that, because that is the exact same as the above. The only difference here is on the ones we were doing, those are just straight hydrocarbons. If it's not carbon, it's a hydrogen. But these are going to show effectively exactly the same thing, and the way that you assess them is exactly the same. So maybe I'll just do one of these. So let's pick this one. Yeah, exactly. I don't feel like it. It's my stream, so I get to do what I want. Ha. Yeah, so as not to end up repeating myself too very much, we're just going to pick this one. So again, we'll just draw it out. So carbon, 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 and bromine. And as the rule goes, when you're drawing out line structures, carbons are implicit whenever, like at the either at the end of a bond or at the vertex of two bonds. Have I done much biochem in my studies? Not a large amount. I had to take a couple biochem courses in my undergrad. So I did like just an introductory one, and then a third-year course on proteins, enzymes, and nucleic acids. And like I know lots of biochemists. They're my friends. They're lovely folks. And because the protein interactions, hell yeah. Oh boy. Yeah, that is so much like bigger stuff that I care to deal with, because it gets gross. It gets hard. Because like so here's my whole view on biochem. I love it. I think it's great. Conceptually, I find biochem to be absolutely fascinating. Because I mean essentially is just like, well, what if we just did a lot of chemistry everywhere? And that's how we came along. And so like looking at it from that kind of bottom up approach, because I've got my theoretical backing in chemistry, I find that fascinating. The lab work itself is like, I mean, I'm not going to say I would rather watch paint dry, but I would rather watch paint dry. biochem labs, they're just the stuff they produce is so interesting, and the work itself is so dull. Just like looking around a biochem lab, I look on the shelves and like everything's either like colorless or blue, um, and I'm just like, so like none of these are like pyrophoric. Uh, I could drink most of these reagents and I'd be fine. Like nothing is going to like, nothing's going to explode. I just like, why are we even here? Story of my life studying cell biology. It's either blue or colorless. Yeah, and I mean like most of organic chemistry. Like I'm a main group chemist, and like main group and inorganic chemistry is what I do, and so all my compounds are like highly colored, very very strongly colored, and it's lovely. I really like it, um, but yeah, organic chemistry as well. Like almost everything is like yellow or colorless, and if it isn't, then you messed up somewhere. Um, but yeah, no, like I've told people a number of times about the biochem lab, and I'm like, like it's just I was doing inorganic chemistry around the same time, and it's like, man, there's so many cool things. Like I can put my compounds in there. It'll be like a deep purple, and then I boil it for a while with something else, and it comes out like just canary yellow. And if I lick it, I'll die. Like that's cool. That's really interesting. I've got stuff that if it touches water, it'll explode. I think it was last week on stream. I was telling the story about how I made a flamethrower out of a flask, and it was one of my core memories. Like this was such a great time. But like that's the kind of stuff that I really enjoy doing. That's just, I don't know. Perhaps I'm just like a little bit of an adrenaline junkie in the lab. I don't think that you can major in chemistry without being like at least a little bit of a pyromaniac. I do not think that's possible. Just want to see. Yeah, so you say cell biology. Like, are you out in the real world and working, or are you in university, or what's your situation there? And while you're working on that, I'm just going to finish this one up real quick. So we're looking at the first carbon in the chain here, and so yeah, in line structures, I was saying the carbons are implicit on the ends of bonds or at the vertex, and all carbons will be assumed to have four single bonds to them. Carbon likes to have four bonds, no more and no less. It can, if it has more, or well, if it has less, then you're using some very harsh reagents. And hi, meet my cat. This is Daphne, and she is the purest soul I think I have ever met, and I love her with my whole heart. You're so good. Third year of a 4-year integrated master's course. That's really cool. Good job on that. So tell me, I'm not familiar with what an integrated master's is. Just let me know what that is, because that sounds all right. Hello, sweetie. But yeah, so I've been at University of Lethbridge for 12 years. I started my bachelor's there, went straight into a master's, and then just I discovered at that point I wanted to teach, and so I'm like, well, gonna need a PhD anyway. So I didn't finish my master's. I just started straight into a PhD. Because I like I met the threshold of self-loathing that you must have in order to do graduate studies at all, especially a PhD. All right, so this carbon being attached to one carbon, one bromine, and two hydrogens makes it primary. All right. You're from the UK. It's where you do an additional year on top of your three-year bachelor's to obtain a degree equivalent to a master's level. That's fantastic. I really, really like that. I wish there was more of that here. Yeah, like I'm in Canada, in Alberta, and so yeah, we don't, as far as I know, really have anything like that. Because yeah, we get our 4 year bachelor's, which usually ends up being 4.5 or 5, because doing it in 4 years is almost inhuman. Um, but yeah, so additional year. So then, for your masters, like, do you have to do like a big research project and a thesis, or a dissertation, or is it coursework, or what's that? Oh, right. Okay. Oh, don't mind me. Okay. So next question is, determine the IUPAC name for each halogen-containing compound below. For the first two structures, also list the common name. Why would I do that? All right. Well, anyways, we'll start with this one. So, when you are going from a structure to a systematic name, the first thing to always do is to identify the principal carbon chain. That's the longest continuous chain of carbons. And in the first one here, it's very easy because there's only 4 carbons and they're all in a row. So we got 1 here, 2 here, 3 here, and 4. I'm actually going to correct myself on that in a minute, but we'll leave it for now. Wrote a review paper this year, your dissertation on cancer immunology. You'll be working on it in your supervisor's lab next year, working on the same topic. Fantastic. Oh, man. Yeah, so you wrote the review paper, so that's all done. So congratulations on that. That sounds really, really cool. It sounds really big, like a big undertaking. I need to write another lab-based dissertation on that. Okay. I gotcha. So you do a research component, and a just like a kind of lit review component, if I'm understanding that correctly. Yeah, that's really neat. Congratulations on getting that done. Very good. Very good. Cool. Yeah. So, do you have any plans for after you're done your degree? Then, like, are you kind of aiming for a job in industry or academia, or and if you don't have any plans, that's completely fine. Yeah, I didn't know what I wanted to do until I was like fully like, you know, a good couple of years into my PhD. So I'm never one to say that you should be in a rush to figure out what exactly you want to do with it. Okay, so hello, Fergster. Nice to see you. Thanks for coming in. So Rosalind, a PhD possibly, but I think about it more in a few months. Totally fair. Yeah, a PhD, like, I've talked to a lot of students about grad school, and what I will consistently always tell my students is that like, if you really want to do this, like, if you get the happy brain chemicals out of doing the research, and if this is like what you want to do, by all means, like do a PhD. That's awesome. And like, if it is, if the job that you absolutely want more than anything else in the world is at the end of a PhD, absolutely do it. I won't join the conversation, but hello, no worries at all. No, never any pressure to interact. But I just appreciate that you're here. Hello. So yeah, I've always told my students. Yep. No, yeah, that's good. Because, yeah, anybody who you know, puts any kind of pressure on someone that, you know, you should do grad school, they're just not right. It's like, if it's not something that you really want to do, or that leads to the thing that you really want to do, I have talked people out of going to grad school, uh, because like if it's just like family pressure, I'm just like absolutely don't. If that's why you're doing it, it's a bad reason and it isn't worth it. Because yeah, like for me, it was like because I never even planned to go to grad school. I was doing my bachelor's degree, and and I said, okay, so I'm going to finish this up, and then I'll go get a job in industry and make adult money, and that'll be the end of it. Well, so I got to the end of my bachelor's. I had some research experience, and I did an honors thesis with my professor, and he gave me a lot of leeway, a lot of independence in this research project, and I just, I really just was, I fell in love with doing the research and like really thinking in depth about a project, and that was when I figured happy chemicals, hell yes, love it. Um, but yeah, so like I decided like I am not going to be content with doing the kind of work in industry that a bachelor's degree would qualify me for, which is basically, you know, it qualifies you to wash somebody else's dishes, and that's about it. So, so I was like, I'll do a master's, and then you know get into a position where I have some input into research projects, and that'll be great. That's the plan now. And then I got into a master's, and in a master's degree, at my institution, like you're pretty much guaranteed to be offered a teaching position. And so it's just like you know teaching some undergrad labs, which is basically just babysitting and making sure that they don't hurt themselves or others in the process. Um, and but I found that like I love teaching. Like I like research. I think it's great. But 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 teaching is where my heart leads me. Like it is, it's very fulfilling to me. It's something I'm really good at. Um, so so I'm like okay, so I would like to you know do something in teaching. I don't want to end up in a career where I'm not teaching. And so from that point, it's like well I mean I better get a PhD then, because I'm not getting a position teaching with a master's. Not, I'll have a better shot at least with a PhD. So, didn't even finish my master's. So I'm like, yeah, don't need it. It's fine. And so just went straight into the PhD, and here I am. And your babysitters were a bit better. Saw some local anesthetic. I have so many questions. How? Why? Oh man. I'm just I'm dying to to know how this happened. Oh man. Yeah. So kind of the moral of the story that I get around to with when I'm talking to students or anybody about this is yeah, don't worry if you don't have it in mind exactly what you want to do, because I sure as hell didn't. And you know, things will work them out. You'll either find out what you want to do, or you'll find out what you don't want to do. Both of which are progress. And I got very lucky, I think, in like finding really exactly what I wanted to do. Had it on your hands and didn't realize, ate some food on your break. Ah, fair. That'll get you. That'll get you. Uh, oh man, that's oh god. Yeah. Any regrets at all? Hmm. 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 Uh, maybe one. I mean, well, okay. So maybe a couple. One is that I think I would take some time off before starting grad school, because I just went straight from undergraduate into my graduate degree. No breaks, no nothing. Just kept on trucking. Because I mean, I I found very commonly that the work environment in academia is quite toxic. particularly with how they're very like productivity based mindsets, and I guess there's always pressure to be productive and to be working, and it imposes a lot of guilt. Like if you're taking any time off at all, it's always in your head. I should be working. I could be working. I could be reading something at least, and uh, so so I guess I most certainly worked way too hard for way too long. And when I was into my PhD, probably in about second year of my PhD or so, I burnt out. I burnt out very very hard, uh, and I was pretty much just unproductive for like 2 years. Well, probably a little more than that. I was severely burnt out for years, and I am in the process still of getting over that. Like I'm just about it into my next month I'll be starting my 6th year of my PhD. So I've gone way over time. Luckily, my supervisor and my PhD committee have been very kind and very patient with that. Um, but for myself and for my own mental health, um, it's been a really rough go, and like that productivity mindset burnt me out entirely, and just yeah, I'm still recovering from it years later, and so yeah, I definitely I have some regrets of like not taking breaks, of not taking care of myself and my mental health, um, but I mean, it's I've been learning, and I've been working really hard on on focusing on my mental health and my physical health. Things are getting significantly better. I'm getting a lot more productive, um, like because I'm taking care of my mental health and working in a way that's sustainable now. Hope things work well. Thank you. I appreciate that. And honestly, it's been going really well, especially the last year and a half or so. I've gotten two major papers published. One just last month. It was like the the major paper of my PhD, and it's the culmination of about 7 years of work, give or take. And that's all done and published now, and now I'm really very close to graduating. So like things are definitely getting better, and they are doing so because I am being very protective of my mental health. I have reassessed my work ethic entirely. Yeah, thank you so much. I really appreciate that. So yeah, I definitely I really hope that you'll go into that with a healthy mindset. Like keep at it, work steadily, work sustainably, but always take care of your mental health, because that is just that it's so incredibly important, because work and school, like those aren't your entire life, and anybody who tries to tell you that should be your entire life can go take a long walk off a short dock. Yeah. All right. Oh, thanks. I yeah, appreciate that. No, I I try to give good advice. I guess because like I've made like so many mistakes, and so I hope I can help people to learn from it, and maybe don't quite follow in my footsteps. And I was having this conversation with someone on stream, well, last week or a couple weeks ago. Um, is that yeah, I remember it. And sorry, this is I'm not ADHD. Everybody else is. Sorry, this brought like 3 or 4 things to my mind that I wanted to say. One of them was that like I've told students over the years, like many times, that like yeah, of course, like I'm better at chemistry than you are. Of course I am. I've been doing this for a long time. I have tried and failed at this stuff more times than you've ever tried. Um, and and it's like making mistakes is just like it's not great. It doesn't feel awesome, but like it's fine. Like the stakes are generally very low, especially in a teaching environment like you know this stream for example, or when I'm tutoring or teaching. I always try to get through to my students that like just like try stuff. I don't care if you don't get it right. Like I'm not going to think less of you as a person if you don't give the correct answer. And if you try stuff and there's you know if there's a problem, if you've done something incorrectly, then that's great because then we can correct that because that like there is like in your procedural knowledge of how to do these things and how to solve these problems, there you know if there's a gap in your understanding and you're not aware of it, then you can screw up on a test or like in a lab when it's you know when you're handling dangerous things. And so it's important that that we you know find those gaps. And so most of my teaching is not like explaining concepts or like you know like teaching the theory of things. A lot of my teaching is like asking my students questions and getting them to work through things and identify like okay, so what do we need to work on here. Of course, it's going to be a little different if and when I'm like teaching classes and all, but yeah, the moral of that story is like it's okay to make mistakes. I promise you, on this stream, in front of the entire internet, I am going to make mistakes. I've already done so in some previous streams, and usually I'll like you know, realize it in between streams, and then I'll come back and like that'll be the first thing I talk about, because I just don't mind making mistakes here because that's how we learn, and I'm very much still learning. And so if I make a mistake, I want to know about it and I want to correct it. Anyways, I'm going to take a step down from my soapbox and finish answering this question. It started a while ago. Okay, so we're going to create a systematic name from the structure of this. We've identified that the principal carbon chain is 4 carbons long. That means that it's got the prefix bute, because we have like meth, eth, prop, bute, pent, based on how many carbons are in the chain. So 4 carbons is a bute chain. They are all single bonds between the carbons. So this is going to end in butane, just referring to alkanes, alkenes, and alkynes, which are carbons with all single bonds, carbons with at least a double bond, carbons with at least a triple bond. Yeah, so this one is going to be butane, and the chlorine on it is... So, we've identified the principal carbon chain. Now we have to identify the substituents. So chlorine is called chloro when it is used as a substituent. Thanks for entertaining my random questions. Almost 3 a.m. here. I should probably sleep. That is very fair. I really appreciate your random questions. Questions make me very happy. Yeah, I hope you get a great sleep. And yeah, if you can come back sometime, I'd love to see you. You have yourself a good snooze. Alright, so this the chlorine here is a chloro group, and so it's going to be a chlorobutane. If I can successfully draw an O, there we go. Alright, and now we have to number the carbon chain so that the principal functional group, or in this case, the only functional group, is at the lowest possible number. So instead of numbering them 1, 2, 3, 4 from left to right, we're going to reverse that and put the carbon number 1 on the right side so that it refers to the chlorine, and this will become 1-chlorobutane. We need that because it could be 2-chlorobutane or 3-chlorobutane if all we had was like the formula, just the element symbols. We wouldn't necessarily know where to put the chlorine, so we have to specify when we turn into the systematic name. Otherwise, it's not systematic, is it? Alrighty. Okay. Alright, so, next one. Again, the first thing is to find the principal carbon chain, which is very easy when they're all just nicely in a row. The numbering on this one is not going to matter because the one and only substituent, the functional group, is attached to the middle carbon. So either way that you number these, it'll be on carbon number 2. So we're not going to worry about. We're not going to worry about trying a different order for the carbons because it won't make any difference. So the functional group here is a bromine, which is just called a bromo group, and it's on carbon number 2. So we're just going to call it 2. Okay, so 3-carbon chain is the propyl, and because all of the carbons are single bonds, it's going to be an ane, an alkane. So it's all fully saturated, which say that it's all carbon-carbon single bonds. So then this one is going to be 2-bromopropane. Very, very good. Okay. Now this one, I should probably keep my colors consistent. Yeah. Okay, so this one we have to find the principal carbon chain. So, two possibilities here. So let's start up here. So we'll start carbon 1, carbon 2, 3, 4, 5, 6. Now there we could go 7, 8, or we could go 7, 8. And this does actually make a bit of a difference. Because okay, so if we go 7, 8, then this group here is just one. There's just one substituent, and it's an isopropyl one. That's going to be on. Well, if that's the case, then it's going to be on carbon 3. Because that would be the order, because otherwise it would be 5, 6 instead of 3, 4. Why did I start where I did? Okay. So, if the question is why did I start here at first, completely arbitrary. Just because I was counting, like trying to count up to see what the longest carbon chain was. But once I started to identify substituents, the rule for a systematic name is that when you're specifying what carbons substituents are on, so like I don't know why I'm pointing at the screen over here, you can't see that. So like with the 1-chlorobutane, initially I had started from the left, 1, 2, 3, 4, but in order to put the substituent on carbon number 1 instead of carbon number 4, I had to reverse that numbering, because we always want to give the substituents the smallest set of numbers that we can. So one way to classify this molecule that we're working on will be to go follow the purple numbering. So there would be substituents on carbon 3 and carbon 4 and carbon 5, 6. If instead, let me just try and make this a little more clear. So if instead we went, instead of going to the left at carbon 6, if instead we went down, we'd go 7, 8, which, gosh, I really have screwed the pooch with these. Hold on. Let me just take back everything I ever said. Okay, 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if we number according to the purple numbering scheme, you get substituents at carbons 3, 4, and 6. If we use the numbering of, if we use the red numbering system, then we get substituents at 2, 3, 4, and 6. And this is what decides which of these naming schemes we need to follow. Now, really, you absolutely could name this compound based on either of these numbering systems. And they would both be valid. You would be able to write the exact structure of this compound from those. However, the most correct way to do this, which is just by the conventions set down by IUPAC, the International Union of Pure and Applied Chemistry, this is the more correct naming scheme because it starts at a 2 instead of at a 3, and that's really like that's all that determines how we need to name this. So just to keep in mind, both of them are valid and will lead you to the correct structures, but the numbering scheme in red that starts at carbon 2 for the numbering system is more correct. Oh, that's great. I love questions in general. And basic questions are the most important questions of all to ask. And like you should, I hope you should never feel silly or stupid for asking just basic questions, because it's so important to just approach subjects honestly, and you don't know what you don't know, and there's no reason to expect that you would know something that hasn't been explained to you. So yeah, you will never ever find any judgment from me for asking a basic question. In fact, like, basic questions are really excellent. It doesn't matter if you're in high school or if you're in grad school. It makes no difference. We are all learning all the time, and every question is worth asking. Okay, so now we've set our numbering system, and now we're going to identify our substituents. So I'm going to clear this up a bit by just erasing those. We'll just remember what our numbering system was. So the principal carbon chain is the one going up here, and so our substituents are here. There's a methyl group. Here there's an ethyl group. There's a chloro group here and a methyl there. Okay, and so this is 1, 2. I'm going to put the numbers back now. 3, 4, 5, and 6, and well, sure, 7 and 8. Why not? Okay, so I'm going to start by naming the principal carbon chain. That's always what you should start with for these. So the principal carbon chain here is 8 carbons long. So it's got the prefix oct. And all of these are carbon-carbon single bonds. There's no double bonds, no unsaturations at all. So this is an alkane, so it's going to end in octane. Now, for functional groups, we've got 2 methyl groups, and they're on carbons 2 and 6. So I'm just going to write kind of the pieces of the name over here, and then we'll arrange them in the name in just a minute. Okay, so we group all of the identical substituents together. So both of these on carbons 2 and 6, both of those substituents are methyl groups. And so in order to communicate that there are 2 of these, we call it dimethyl. If there were 3, we'd say trimethyl. More than that, we'd say tetramethyl, pentamethyl, so on and so forth. But you have to specify how many there are and on which carbons you find them. So these methyl groups are 2 on carbon 2 and carbon 6, so it's 2, 6 dash dimethyl. So yeah, commas between numbers, dashes between numbers and letters. So that's those ones taken care of. There is an ethyl group attached to carbon 3, so it's going to be 3 ethyl. And a chlorine on 4 is going to be 4 chloro. Okay, so this is all of our substituents. And now the order that they're named in the systematic name is not dependent on the numbers. It is dependent on the alphabetical order of the substituents. So the C for chloro is going to be the first. The E for ethyl is going to be the second. And not the D, but the M for dimethyl is going to be in the third position. So when we're figuring out the order of the substituents, the alphabetical order, you never take the prefix into account. So di is the prefix to methyl to communicate that there's 2 of them, but the substituent is the methyl group. So we use that letter. So we're going to say 4 chloro dash 3 ethyl dash 2 6 dash dimethyl. And I'm now going to erase these and half of the other thing that I was trying to write. And then octane. Okay, and so this is the entire name for that compound. Yeah. All right. All right. Now for this one. Again, we'll, as always, we start by identifying the principal carbon chain. That's going to be number 1 there, 2 there, 3, 4, and 5. All right. So there's 5 carbons in the main chain. Cheeses to cakes. Good to see you. Hello. I hope you're doing well. Just going over naming some compounds. Yeah. Okay, so we got the principal carbon chain. I am doing very well. Very well. It's the weather's finally gotten nice here. It seems kind of like vaguely spring-like. As the frozen wasteland of the north is starting to thaw. We're doing okay. All right. So, principal carbon chain is 5 carbons long. That means it is going to have the prefix pent. They're all saturated, all carbon-carbon single bonds, so it's going to be a pentane. Now the substituents, we've got 2 methyl groups, we've got a chlorine, and we've got a fluorine. And is a hazard of having 2 cats and a dog is that at any given time there's very likely some hair in my mouth, and I don't love that. But that's okay. All right, so we've got 2 methyl groups. So again, this is going to be dimethyl, because in the name, you have to think about this as in like you don't have this structure in front of you, and so every part of this molecule has to be specified in the name. So we have 2 substituents here that are methyl groups, so it must be dimethyl. And so both of these are attached to carbon 2. So it's 2, 2 dimethyl. Because again, if you were just reading the name, these methyl groups could be put anywhere, so we have to specify where each one of them is. And so they are both attached to carbon 2, and so it's 2, 2. The chlorine is attached to carbon 3, so it's going to be 3 chloro. And the fluorine is attached to carbon 4, so it's going to be 4 fluoro. Alright. So, now we have to set the alphabetical order of the substituents. And the first one up is going to be C for chloro. Next one is F for fluoro, and then M for dimethyl. Again, we do not take the prefix di into account when we're setting the alphabetical order, because we name them based on the substituents, not the prefixes. So then this whole mess becomes, not that, nope, there we go. Ah, crap. Whatever, it's fine. No, it's not. I can't deal with it. Okay, so going to have 3. This is going to disappear, so let me just come over here. So 3. God, I can't write. 3 chloro dash 4 fluoro, and then 2 dimethyl pentane. Yeah, exactly. Yeah, and these are pretty small and pretty simple compounds that we're working on here. But if we were working on like a significantly larger compound, like lots of like pharmaceutical compounds come to mind, you can have like a whole bunch. You can you could have 6 or 8 different types of substituents, and sometimes multiples of those. And so you might have several that are like a 3,4 dichloro 6,6 difluoro something or other. And so if you named if you set the alphabetical order based on the prefixes, you'd be well, you couldn't, right? Because you'd have a whole bunch of of groups that are di, you'd have some that are tri, and that just doesn't. It's not helpful for distinguishing them. So yeah, we always leave that out when we're talking about or when we're setting alphabetical orders. That's the one. Okay. All right. Do I want to do these? Maybe. Although, cheesiest of cakes. I'm glad you're here because I was doing some more thinking and looking up the concepts of like Boltzmann distributions and like temperature and heat and those differences. So just to catch Ferguson up a bit on what we were talking about. So the question from Cheesiest of Cakes was that right, no worries, take your time. So the question was, and correct me if I'm wrong, if I'm not remembering this right, but it was like, are heat and temperature the same thing? And the answer to that is no, because heat is a measure of the energy of like an energy transfer. So like it's descriptive of like the energy of molecules. Like if you have a little cube of like a sealed chamber with gas in it. They weren't. Heat and temperature. Yeah, no. Heat and temperature are different things. It's like the heat is like basically a measure of like the energy of the molecules in that container, in that volume. Whereas temperature is something different. Temperature is effectively say like basically like the average energy of molecules in a system. Weight versus mass, no, not so much. Like we're talking about it has to do with like mass is relevant because you can have gases that are different masses, but I think we just assume kind of uniformity. But mostly, what temperature is descriptive of in a sample of gas is the kinetic energy, so like the speed of the particles, and that number, the average speed of like gas particles around you, is going to mess your brain up a little bit. So temperature was average temperature of molecules. No. So temperature is the average energy of molecules. So heat affects temperature, but heat isn't itself temperature. So they're not the same thing. My apologies, Ferguson. I misunderstood. Weight versus mass. Yeah, actually, that is a pretty good analogy. Yeah, like weight is effectively a measurement of a gravitational force on a mass, like that acts on a mass, and so that's what we measure. Is we measure the weight to infer the mass of a thing. And so yeah, similarly, we measure the temperature of a system in order to infer the energy in that system. And yeah, so I was one thing I was talking about, because so if we just have kind of a general energy diagram. So on the y-axis here is I think it was like number of molecules of Also, can we please all just like start a petition to pronounce molecules in a more interesting way? Because I think it should be like we should do as the Greeks do. So like, if this was like a Greek mythological name, it would be Molecules, and I just think that's so much more fun. Um, so okay, so this is one way to depict the temperature and to explain how temperature is descriptive of like the energy of molecules or the speed of the molecules. And so it's saying like this is the most probable speed. So like that the peak of this curve here is the highest number, like it contains the highest number of molecules at a certain speed in a system. I like molecules. I was stand by here. You know what? Fair enough. I respect that. The most likely speed for a molecule to be going in this gas sample is right here at this speed. But then there's then there's an average speed, and then up here there is a value called the RMS, and so this is the root mean square speed is what we usually use in thermodynamic measurements of this. Root mean square. So the root mean square speed, and so I was reading about this a bit today, and I wanted to explain a bit about it because I think it's really interesting, and it's something I haven't looked at since like second year chemistry or so, which is a little while ago now. It's roughly a decade in my rearview mirror. That's depressing. Okay, so there's a I'll explain what the root mean square speed is, and then why we use it. So root mean square. So this is 1 over n. Now what was it? Is what were those terms? Oh bollocks! Don't mind me. Just things are going exactly according to plan. I've got a better way to explain this. Okay. Don't worry about the equations. I don't like them anyways. Me and math, we have an understanding. I have a great deal of respect for math. I'm just not good at it. So I'm going to basically pretend that it doesn't exist. But, so, root mean square speed. It's, you take the average speed of the molecules in this sample. So that's the mean. You take the mean, and then you square that value, and then you take the square root of that squared average. So basically, you take the average, square it, and then take the yes. RMS and computer AI, fantastic. Okay, so I'm glad because I am not explaining this well, and so I'm glad you have at least some idea of what's going on. RMS either way, pretty cool. Yeah, I'm doing a crap job of explaining what root means square is, but I do understand the concept, and so we'll go over that now. So the reason that we do this odd thing, we take a value, we square it, and then we take the square root of it. It seems a little silly. It seems redundant, but it's not. It does it has a very important function, and so that function is that so every molecule has a velocity, and multiply them. Yeah. So we take the average. So we add them together. We divide by the number of entries in the series. Well, we sorry. Do we root mean square? Yes. We take the values and we square them, and then we add them together, and then divide by the number of entries. So that's just taking the average. That's how you do any average. And then you take the square root of that number. So I'm gonna try this again, and we'll see if it goes as badly as it did the first time. So 1 over n times v1 squared plus v2. This is going good, actually. I like this. Squared dot dot dot. Okay. Hey, I did it. Okay, so basically it's taking the velocity of molecule 1 squared plus velocity of molecule 2 squared, so on and so forth. And you take all these velocities and you square them, then you add them together, then you multiply them by you divide them, you multiply by 1 over the number, but you divide by the number of entries, and then you take the square root. So squaring and then taking the square root seems redundant, but it isn't, because there's these two properties, speed and velocity, and these are different things. So speed is just bid mess. You may have to help me out with this one. I that rings a bell. It feels familiar, but I don't know what that stands for. So speed is just like let's say 30 meters per second. So it's like 30 meters per second. It's a length over time, which is speed, and the difference between that and velocity is that velocity would be like 30 meters per second in a specific direction. So this is the difference between speed and velocity. Speed is just a magnitude. It's called a scalar quantity in physics. So it has no directionality. It's just like it just has a magnitude of the value. So it's just a speed. But velocity is a speed in a specific direction. And so you could say like if it's going like if it's on an XY axis, then it is 30 meters per second X and 0 meters per second Y. Whereas like something like this, I meant to make that a different color. This would be like negative 30 meters per second X. I remember vectors as direction and magnitude because of that one Despicable Me scene. Oh man, I don't know which scene because I've only seen Despicable Me once. That was a very long time ago. But I'm super glad that you've got a grounding in what vector quantities are, because yes, the speed is a scalar quantity, and velocity is a vector quantity. So when we're talking about molecules of gas in some sealed chamber, some of them are going to be going that way, some this way, some that way, so on and so forth. So they've all got a velocity, and that's important, because so when we're adding them together, some of them may have a velocity with a negative x component and a negative y component. Some of them may have a negative x component and a positive y component, or any other mixture. And so basically, what taking a root mean square speed does is first you square the value. So if you take this minus 30 meters per second and square it, and the 30 meters per second x and square it, you get 900 meters squared per second squared. So if we were to add them and take an average, you would now be adding two positive numbers. Because if you added them like this, 30 meters per second plus negative 30 meters per second, then you just get 0 meters per second. Whereas when you square it, now you've got now you've got two positive values. So basically, you by squaring it, you're eliminating the negative signs. Like you're making all of the values positive so that they're all additive. Because when you're looking at the temperature of the system, which is describing the energy of all the molecules in it, they're going to be going in all sorts of different directions. But by squaring the values, you no longer care about what direction they're going in, because it's not relevant anymore. It's basically like taking similarly like taking the absolute value of a thing. Then you're adding all those together. So if you take this value 900 plus 900, so you get 1800 meters squared per second squared, divided by 2, because there were 2 entries here. 900 meters squared per second squared, and then take the root of that, and it becomes an average of 30 meters per second. So by going this route, you get an average of 30 meters per second, because it doesn't care what direction these are going, just that both of these things have a speed of 30 meters per second. Whereas if you try to add the vectors together without squaring them, you come out to an answer of 0. And that's not actually descriptive of the system. So that's what root mean square speed is about. It's about removing the directionality from the equation here, so that everything's kind of on a level playing field, and it doesn't matter what direction it's going, just the energy. And that ends up being higher than the average speed. Because again, the average would be just adding things like this and coming out to answers that aren't really useful thermodynamically. And so you're going to tend towards higher values with root mean square speeds, but it is an accurate representation of the energy of a system. All right. So I tell you, I've been going for about an hour and a half, and my brain is getting a little bit toasty. So I think I'm going to actually call it a night here. Um, but yeah, I really appreciate y'all coming to hang out for a bit. Oh, thank you so much. Appreciate it. Uh, yeah, and I will be back doing this again on Friday. I thank you so much for just hanging out, asking some questions. Always really appreciate that. And yeah, all y'all have a great night and take care. Okay, bye.